Acetoacetic ester synthesis. It's a way to make what are called substituted or alkylated acetones. Quick review. We should remember that we can make ethyl acetoacetate, which is a beta keto ester, via Claisen methodology by the self-condensation of ethyl acetate. Being a beta keto ester, the alpha carbon shown right there is doubly alpha, and so its hydrogens are even more acidic than, say, ethyl acetate, pKa value of about 10. So with a base like ethoxide, we can, with one equivalent, generate full conversion to this enolate. The enolate, like all good enolates, it is a good nucleophile, and with the right SN2-like halide, we can get the enolate to do a nucleophilic attack, displacing the chloride, resulting in an alkylated product. And if we wanted to, we could repeat that sequence, mainly ethoxide and another halide, and we could easily make a di-substituted product. And note that R or R prime could be the same or could be different. This reaction is going to be much more facile than, say, the regular Claisen reaction, because again it's doubly alpha, that hydrogen, and the real utility shows up now because we can simply take hydrolysis conditions, acid and water, and hydrolyze off the ester to its carboxylic acid. So now we have a beta keto acid, and these, with mild heating, say at 50 or 60 degrees, undergo loss of carbon dioxide. And when we lose carbon dioxide, the final product is what's called a substituted acetone. The mechanism of the decarboxylation is interesting in the fact that it happens due to, again, the acidity of, or the formation of an enol. So mechanistically, we can see the elements of CO2 right there, and movement of a proton from that O of the acid over to the ketone O, with loss of CO2, provides the enol form plus CO2. And of course, we already know that that enol, it could just as easily have been shown as its ketone form, which is again a substituted acetone derivative. So in essence, acetoacetic ester synthesis takes advantage of an ester group making the hydrogen alpha more labile and more facile reactions to do your alkylation, And then lastly, the ester can be hydrolyzed in acid to the acid. And since it's not just a normal acid, but a beta keto acid, these are prone to decarboxylation to give us substituted acetone. This avoids using a strong base like LDA and then the halide to do your alkylation that way. And anytime we cannot use a very, very strong base and the expense that comes along with that in industry, that's a really important reaction. So to summarize, the beta keto ester, ethyl acetoacetate, can easily be deprotonated to make an enolate. Alkylation with a suitable halide provides a substituted acetone or disubstituted acetone derivative after hydrolysis and decarboxylation.